Thin film interference. Right, this is thin film interference. We have a very thin layer of oil, and you see this beautiful rainbow effect due to this disgusting puddle of oil which is mixed with water. But it looks nice. It's disgusting, but it looks nice. And here we have another kind of thing here. This is when you blow bubbles, you get the same effect. But this is much nicer. Oh, and this is beautiful. Look at this. You've got all these yellows and blues and purples and so on. Okay, so what is all this about? Now, what happens here is that we have a layer of oil below the layer of air. There's a refractive index of the oil, which is we call N2. The refractive index of the air is N1. So this is what's called a thin film. This is called a thin film interference, and it's called that because it has two things. One is a thin film, like the oil, and because we have this amazing property of light, which is called interference. So the light comes in and it gets reflected. So we call that the reflected light. However, between the air and the oil, we will get some other property, which is refraction. The light refracts as it goes into the oil, reflects off the bottom, and then comes out again. Okay, hold on. The light which has gone through the oil has gone a different distance to the light that is reflected from the surface. And if there's a certain path difference, we could get interference. So, if the rays are in phase at that wavelength, you will get constructive interference, so that the color that you see at this angle, in this direction, will be the color that is interfering constructively. Other colors will not undergo constructive interference, so they won't be seen as clearly. So, if you look at it at different angles, then you will see different colors. Like this. Ooh. Now, if you look at this, there are a number of geometric calculations that you would need to do to calculate all this. Because this color that you see depends on the angle of incidence, it depends on the refractive index of the second and the first medium, it depends on the thickness of the oil, and so on. It gets a little bit complicated. In fact, it looks a bit like this. However, the IB have been nice to us. Fortunately, the syllabus says that the treatment of thin film interference is confined to parallel-sided films at normal incidence, which means we just take it coming along the normal, which makes it much easier to do. So this approach is basically an approximation, because we're treating it all as being a normal phenomenon, but of course it happens at different angles. Now let's look at this again and see if we can come up with the maths that goes with this. So we have this oil which has a thickness d. However, when the light goes into oil, it refracts. It goes slower, which means the wavelength is reduced. So we have what's basically an optical distance which is actually greater than d by a factor of n. So since it goes slower in oil, we're interested in the distance nd, not d, because we're interested in the number of wavelengths. So the light comes in, the light gets reflected. Oh, there's something odd that happens here. If you remember this experiment, when you had a rope attached to a wall, the wave, when it goes down the rope and comes back, gets inverted. There's a phase shift of pi radians, or in other words, half a wavelength. And that's what happens here. It's basically because the oil is a denser medium than the air. So the reflected light undergoes a phase shift of pi radians, a bit like a wave reflecting from a fixed rope. Now we will look at what happens in the oil. We know that some light will be refracted and reflected off the bottom. By the way, if there were another medium here, it could be that this also undergoes another phase difference, but in this case it doesn't. So this is refracted out. Now this extra distance that it travels is going to be nd times by 2, so 2nd, not second, 2nd. Now if 2nd is a whole number of wavelengths, i.e. 2nd is equal to m times by lambda, then we will get destructive interference. Remember that the first ray, which is reflected from the surface, has undergone a phase shift of pi radians, or lambda over 2 already. So there's basically, you're going to get a crest meeting a trough effectively, so you'll get destructive interference. However, if the second, however, if 2nd is a whole number of wavelengths plus another half wavelength, given that the reflection from the surface has got an extra half wavelength, then you will get constructive interference. So 2nd is equal to m plus half times by lambda. Now here's an application of this. We put a thin coat of material onto glasses to stop the reflection. Now the pair at the bottom do not have anti-reflection coating, so the light is reflected, 10% is reflected and 90% is transmitted. The top pair, however, have a bit this ghostly kind of color there, but most of the light has been absorbed because it's basically undergoing destructive interference. So here we get 2% is reflected, which means that the other amount will be transmitted. And here we have again, why do you think that we have lots of layers as you move down this this wire here to it being kind of colorless here? What could be going on there? Now there's a very good worked example in the textbook. I suggest you look at that. There's a bit of a twist to it, so you need to think carefully about this problem, and there's a twist, so look at it carefully.